Hello, I'm Ryan from the University of Illinois. Thank you for joining me virtually at WASPAA 2021. Today, I'll be talking about remote microphones, which are wireless accessories for hearing aids and cochlear implants. It's often hard to hear in noisy environments like a crowded restaurant, and it's even harder lately thanks to face masks. Listening devices can't do much to help on their own because their microphones are in the earpieces, so they get the same noisy sound as the ears. But with a remote microphone system, we can stream sound directly from the talker to the listener's ears. For example, here's the remote mic that works with my hearing aids. If I'm out to dinner with someone, I can ask them to put it on and it will stream to my ears. There are also directional microphones, like this one, that the user can point at what they want to hear. Recently, a few companies have introduced microphone arrays that sit on a table and beamform to different talkers. Wireless assistive listening systems are also common in classrooms, in part because they're often legally required. There's strong clinical evidence that remote microphones help people hear better in noise, and they're especially helpful when the talker is wearing a face mask, but they don't seem to be used much outside of education. That may be because most commercial systems are designed for one-on-one conversations rather than group discussions. My hearing aids, like most others in the adult market, can only pair with one microphone. Some classroom systems work with multiple mics, but only one person can talk at a time. That might work in school where kids are taught to take turns, but if I'm out to dinner with my friends, people will talk over each other constantly, so I need a system that works with multiple talkers at once. But I don't want the system to just add the signals together. It needs to mix them in a natural-sounding way. That way, the human auditory system can use its built-in source separation to follow the conversation. Commercial remote microphones send the same signal to the left and right ear. That's how you're hearing this presentation now, which is fine for a virtual conference, but it wouldn't sound right if we were in a room together. Humans rely on acoustic cues like interaural time and level differences to localize sound. Those spatial cues are especially important for group conversations because they help us separate speech from different talkers. We also want to preserve at least some of the room acoustics so that the system sounds natural. Ideally, our system would combine the high signal-to-noise ratio of a remote mic with the realistic acoustic cues of earpiece mics. That is, the processed signal should sound just like it would at the listener's ears, but without noise. Some researchers have proposed adding spatial cues to a remote mic signal by localizing the source and then simulating a head-related transfer function. But the listening device has microphones on the ears, so we don't need to simulate anything. Instead, we can use an adaptive filter to match the magnitude and phase of the remote signal to the sound at each of the earpieces. The filter takes the remote mic signal as an input and produces a binaural output, and it adapts as the listener and talkers move. First, I'll explain how the system works for a single talker, then show how it can be extended for multiple talkers. Let's start with a few assumptions. First, we assume there is no transmission delay, so we can use a causal filter. Second, we assume that the remote mic has a much better signal-to-noise ratio than the earpieces. This system does not do beamforming, source separation, or other noise reduction, so we need to start with a clean signal. Finally, we assume that unwanted noise signals are uncorrelated between the remote mics and the earpiece mics. This correlation assumption is critical for our system, and we analyze it in detail in the paper. Here's the adaptive filter for a single remote microphone. This is a binaural system, so there's one output for the left ear and one for the right ear. The input to the filter is a low-noise remote microphone signal, and the reference it tries to match is the noisy earpiece signal. Because the noise is uncorrelated between the remote and earpiece mics, the adaptive filter can't predict the noise, only to target speech. This looks a lot like an adaptive echo cancellation system, except that we want to isolate the signal instead of cancel it. In our experiments, we got good results using the least mean squares algorithm, but of course one could also use a more advanced adaptive algorithm. Here's a demonstration for a moving talker in a noisy room. The remote microphone is a lavalier clipped to the talker's chest, like the one I'm wearing now. You'll be listening through the ears of a binaural dummy head, so I suggest using headphones. First, you'll hear the noisy mixture at the ears, then the unprocessed remote mic signal, and finally the binaural filter output. Pay attention to the spatial cues as the talker moves back and forth. When the sunlight strikes raindrops in the air, they act like a prism to form a rainbow. The rainbow is a division of white light into many beautiful colors. These take the shape of a long, round arch, with its path high above and its two ends apparently beyond the horizon. There is, according to legend, a boiling pot of gold at one end. People look, but no one ever finds it. When a man looks for something beyond his reach, his friends say he is looking for the pot of gold at the end of the rainbow. Throughout the centuries, men have explained the rainbow in various ways. You can tell that the processed signal has much lower noise while still preserving spatial cues. Now, our goal is to build a system for group conversations, so let's extend this filter to multiple microphones for multiple talkers. There are two ways we could implement the system, and they each have strengths and weaknesses. First, we could put one mic on each talker and use a separate binaural filter for each one. With wearable mics, it's easy to track the talkers as they move around. The spatial cues might lag behind as each filter adapts to the motion, but we'll still get a high signal-to-noise ratio. We can also apply different processing to each talker, for example, to boost a quiet talker more than a loud one. The disadvantage of this system is there can be crosstalk distortion if the mics get too close together. The second option is to jointly process all the remote microphones. This method makes sense if the talkers are close together and we have a microphone array in the middle. All the mics capture different mixtures of all the talkers. The binaural filter is a mapping from these mixtures to the ears, so it doesn't suffer from crosstalk. You can think of the joint filter as a sum of binaural beamformers, one for each source, but we don't actually need to calculate those beamformers. In fact, the adaptive system never separates the sources at all. It leaves that to the human auditory system. The filter will adapt to whatever sources are strongest near the array, so talkers can freely join and leave the conversation. The downside is that we can't control what sources the array will pick up, and we can't apply different processing to different sources. It's most appropriate when we want to focus on sounds in a certain area rather than on a certain set of people. In the paper, we describe experiments comparing the joint and separate processing approaches in different scenarios. Separate processing tends to be better at rejecting noise, but joint processing is better at preserving spatial cues. Here's a demonstration of the joint system with 3 talkers of interest surrounding an array of 3 directional microphones in a noisy room. This time, the talkers are standing still, but the listener is moving. To get repeatable data, we placed the dummy head on a turntable and made recordings as it turned. First, you'll hear the clean speech from the 3 talkers as recorded by the ears, then the noisy mixture, and finally the processed signal. Pay attention to the spatial cues as the head turns to the left.
There's a story.
This is the window.
He was jailed for
5 years.
Mr. Ferguson is Prime Minister after 7 years.
Then
We must
suddenly
provide a
they
long-term
weren't.
solution. We must provide a long-term solution to tackle this.
Other members of the
Suddenly
family
they
were
weren't.
too upset to
Suddenly
comment last
they
night.
weren't.
Other members of the family
However,
were
they
too
continue.
This
is the window.
Now this series
He was
is
jailed
today.
for 5 years.
Medical vision distributed good.
Then
Not
suddenly
lapsing
they
called
weren't.
materials.
His mom
There was a policy which is work
Other members of the family
They were
were too
urged to
upset
get
to
themselves
comment
in
last
order.
Other members of the
However,
family
he
Too many
continued. This is the window. He was jailed for 5 years. Help is needed.
after 7 years.
Then suddenly they weren't.
We must provide a long-term solution to tackle this.
Other members of the family were too upset to comment last
Other
night.
members of the
However,
family were
they
too
continued.
The system noticeably reduces noise while preserving the spatial cues of the talkers. Remember, this system is not doing beamforming, source separation, or noise reduction, just textbook adaptive filtering. Remote microphones are a powerful tool for people with hearing loss. They let us choose exactly what we want to hear, and they work reliably even in crowded, dynamic environments where noise reduction algorithms would be helpless. In this work, we showed how an adaptive filtering technique lets multiple remote microphones work together with the listener's hearing aids or cochlear implants to create a seamless, immersive listening experience. By removing background noise while preserving acoustic cues, it supports the auditory system's natural ability to process multiple talkers at once. We hope that this work will make remote microphones even more useful for group conversations. Thank you for watching. If you'd like to learn more about our work, please visit the Illinois Augmented Listening Laboratory website. You can find me on LinkedIn, YouTube, and Twitter at Ryan M. Corey.